Hey, I think it's time to get started. Is everything okay online? You can hear me on Zoom, live stream. It's good? Okay, let's get started. I guess as expected, today we have a small crowd. That's good. Yesterday we had no lecture, so it's kind of odd to have one day, but it's great that you guys are here. Okay, today we're going to continue the memory systems lectures we started. We're going to build the memory hierarchy today, but before that I want to complete the memory technology lecture and the organization lecture we had last time. And these are tightly integrated, like memory technologies are tightly related to the why we have memory hierarchies today. Okay, just to remind you, you have another extra assignment, let's say a freebie, but do a good job to get the credit, let's say. And these are the readings. I've already discussed this. We're going to discuss this caches today, and we're going to heavily use some of these readings. But let me just wrap up memory technologies. If you recall, we said memory technologies consist of banks for multiple reasons: to reduce latency, to improve throughput. And this is a two-dimensional storage or memory array that's common to many technologies. Many technologies are organized using these storage arrays. And then if you look inside the storage array, there are smaller storage arrays. And if you look outside, we basically combine these storage arrays to get larger structures, right? So if you recall, we had rows and columns. And whenever we actually want to access something, we first need to drive the row, essentially access a much larger row than what we really need to access, which is the red part over here. And that's called word line driving, essentially. And then this enables the bit cells to be connected to the bit lines. So as a result, you read those bit lines to some sense amplifiers. And the function of the sense amplifiers is really to amplify the raw data and sense it, figure out what that value is. Because usually the data is stored in some analog value, as some analog charge, for example, charge level. And that needs to be converted to some digital value so that we can make use of it in the digital computer. You can think of it this way. It's charge level or resistance level or some voltage level, as we will see in some other technologies, some other things soon, but we don't go into a lot of detail on those. And then among the larger row, then we need to figure out which data we really need. And that is specified by the column address. So you have a row address to activate the row, and then you supply a column address to get the data that you really need across that large row. That large row can be 8 kilobytes, for example, but I want only 1 byte out of that row. And that is done using this column decoder, which is essentially a multiplexer out of the sense amplifiers. And then you get the data out. And then you need to prepare the array for the next access. This is called pre-charging, such that you can activate some other row and then sense the data values in that row reliably. That's the idea of pre-charging. And this depends on the memory technology, which we will not go into a lot of detail. If you're really interested in how these operate, you really need to take an advanced architecture course that talks about how these technologies really operate and what are their limitations, etc. But this is really the memory bank organization that we have in all of our systems. And SRAM essentially follows this bank organization. Inside the bit cells, you see something like this, basically 2 cross-coupled inverters and 2 access transistors and 2 bit lines, as you can see, bit line and bit line bar. And we talked about this, so I will not go into detail over here. So I'll go through this relatively quickly. One thing that differs between SRAM and DRAM is how many bits of address you can supply concurrently to the array. Because SRAM is normally on chip with the processor, you don't need to go off chip to access an SRAM chip, a separate SRAM chip. Wires are plentiful. Wires are really plentiful in a single chip. When you go off chip, wires are not plentiful because you need to actually drive the IO pads, right? You need to go outside. So as a result, you can supply both the row address and column address, as it's shown over here concurrently. DRAM is essentially very similar. You can look at the array over here, at least the basic array. But inside the array, you see these bit cells that look like this: capacitor and an access transistor and a single bit line, as you can see. And you can see that in DRAM, the address is divided to row address. This is called the row address strobe in DRAM terminology, and column address. And you supply the row address first, and then send an activate command. And when appropriate, you supply the column address next and send the read command coming out of the sense amplifiers there. And these are dictated by timing parameters specified by DRAM manufacturers today. And the reason why we supply the row address and column address in separate cycles, well, one of the major reason is because this is a chip by itself, and it's limited by the number of pins that you can put. So if you want to supply the row address and column address in parallel, you need to double the number of bits that you need to use to supply address with. But if you actually supply it in consecutive cycles, you supply n bits first and then m bits next in some other cycle. So you actually save some number of bits, some number of pins essentially. And usually these are somewhat equal, so you save half of the pins. Does that make sense? So these are design decisions that actually are made in memories that are somewhat dictated by technology, because you cannot manufacture this thing nicely, let's say, in a logic process that we manufacture our chips with. Whereas SRAM, you can do it because SRAM is essentially logic. There's no capacitor over here, as you can see. And sensing is also simpler here. As a result, we make some choices that enable us to go off chip. Now, 3D stacking technologies make this trade-off different, but we're not going to talk about that as much. And this slide we discussed also, DRAM and SRAM have these different trade-offs, and this is going to enable us to build a hierarchy out of them. I will not go into the details because we discussed all of these in the last lecture. But I will mention something that we did not discuss as much in the last lecture because we were running out of time. I will talk about this, some other memory technologies. So memory technologies are not limited to SRAM, DRAM, flash memory, as we will very briefly see, or tape. There are other memory technologies that sometimes people try to make happen, let's say, and phase change memory is one example. This is interesting because this memory has been around since 1960s. It's used in rewritable CDs, but more recently, people have figured out how to actually read it very reliably using essentially some special access devices, very reliably and fast, as opposed to doing optical reading. If you know how to rewritable CDs operate, they're optical. So basically, this is there's some material, phase change material, and this is the bit cell essentially. You construct the bit cell using phase change material. It could be chalcogenide glass. It could be different things, but it exists in two states. Amorphous state has some characteristics, and crystalline state has opposite characteristics essentially. In the amorphous state, this material have low optical reflexivity. So if you shine light on it, it doesn't reflect it as much, and high electrical resistivity. So if you pulse current through it, it basically goes through relatively slowly. In the crystalline state, you have essentially exactly the opposite characteristics. This has high optical reflectivity and low electrical resistivity. And in rewritable CDs, the reading mechanism is optical. So you shine light on these devices at a higher abstraction level, of course, and you basically figure out the reflexivity. And based on that, you decide whether the bit stored is 1 or 0. So these two states represent 1 or 0, right? So this is how you can represent things. This is another analog representation potentially, right? But the reading mechanism is optical. So more recently, people have developed a lot of reading mechanisms that enable us to detect essentially the current out of this, essentially detect the resistance that's stored over there based on that current that's flowing. And as a result, people have manufactured these in the form factor and also reading mechanisms that are compatible with what we use for main memory. So that's beautiful. So a lot of work has been done. And as a result, potentially this could replace DRAM going into the future. We'll see if that happens. It's still very speculative. I'll show you a paper that we wrote in 2009 that was basically relatively pessimistic for good reason. But you can see that today we have DRAM, but DRAM has some undesirable characteristics. Why don't we actually have DRAM and phase change memory together hanging off a CPU? MC is the memory controller over here. And maybe in the future, if this technology is very scalable and nice, it'll be less costly than DRAM and will have good characteristics. So maybe in the future, we'll have completely phase change memory based main memory. That sounds good. And that's what we discussed in 2009 as an idea. And there have been a lot of work that was done related to this. Intel actually manufactured it as a real DIMM that you can still buy in the market that enables you to have very large capacity memory, because this can be manufactured actually as very small bits compared to DRAM as well. And also more scalable, because DRAM has a lot of problems like refresh, retention, etc. This memory doesn't have some of those problems. Now, unfortunately, it has other problems. That's why it's not, it still needs to be worked on, if you will. So as we discussed very quickly in the last lecture, unfortunately, this memory is still slower access because of the reading mechanisms, which we will not go into. Basically, you need to heat and cool the material, the phase change material, to change the phase of it. So you can see that the mechanism to write data is very different, right? You actually heat and cool. In DRAM, it's different, right? You basically charge and discharge the capacitor. That's how you read and write, or write and read. So, but the advantage of this is it's higher density. It's much more scalable. DRAM is lower density. DRAM requires refresh. This doesn't require refresh. This is actually non-volatile. It's very similar to flash memory in that sense. So that's good. That's the this point over here, non-volatile. As DRAM, it actually has a lot of manufacturing issues, different from logic. And it's also less mature because people have not manufactured it as much. DRAM is being manufactured since late 1960s, whereas this is being manufactured since, let's say, late 2015s or so. And then one big downside of this sort of memory is it has endurance problems. So DRAM doesn't have any endurance problems as we know it, or it manifests itself after many number of writes. Whereas this technology, if you do, let's say, 10 to the 9 writes, updates to a cell, you cannot read from that cell anymore or write to that cell anymore. So essentially the cell dies. You can think of it that way. This doesn't sound very good, clearly, right? You lose some memory if you keep writing to it. Okay, but these technologies exist actually. Flash memory is very similar. In flash memory, endurance problems are even worse. In flash memory, in some flash memory today, after 1,000 writes, the cell dies. But we use flash memory all over the place, right? So there are mechanisms. Memory controllers are smart enough to actually make sure that the storage works, even though it has this downside. But if you want to expose that main memory, maybe that's not an easy thing to make work, because main memory gets exposed to lots of writes because of the way we design the memory hierarchy, right? We don't write everything to storage, as we will see today also. Okay, and also energy is an issue. DRAM is actually much lower energy compared to phase change memory. I'll give you some numbers later on when we motivate the memory hierarchy. But I just want to cover this because it's important to critically think going into the future. I don't want you to take away that there are only 2 memory technologies, SRAM and DRAM, and we're done. That's not true. There are other things that people have been actively working on. I'm going to actually show you a couple more. And there are other things that may come up, and this may disrupt the hierarchy significantly, as I've kind of shown you over here. We'll see if it happens still. Okay, so one thing that I will discuss related to these technologies is today's memory technologies that have been successful are charge-based. On the memory and storage side, DRAM and flash are both charge-based. You essentially write data by capturing charge in some capacitor, or in flash memory case, it's a floating gate transistor. Again, I won't go into a lot of detail here. And then you read data by detecting voltage. Whereas these other technologies that are more scalable, fundamentally more scalable, are actually more resistive. Essentially, you store resistance, and you write data by pulsing some current, and you read data by detecting resistance. And this actually has been shown to be much more scalable, but manufacturing is another issue, of course. So manufacturing needs to mature to actually make these work. So these are 3 interesting technologies. There are more. Again, this is, let's say, more speculative, so I will not go into a lot of detail. We discussed phase change memory. You inject current to change some phase of a material, and resistance is really determined by phase. That's how you store data. In magnetic memory, you inject current to change the polarity of a magnet. So essentially, this is magnetic. You've learned about magnetism probably. And resistance is determined by the polarity of the magnet. So you compare the polarity of the magnet to a reference magnet, and whether you store a 1 or 0 depends on whether the polarity is essentially the same or opposite of the reference magnet. And in memristors, RRAM, ReRAM, some other memory technologies that are also interesting, you inject current to change some atomic structure of the material. And in some cases, for example, resistance is determined by atom distance. So you can see that these are very different mechanisms to store data and also read data. I can also add more over here, like people are actually looking at glass-based, some sort of glass-based memory storage technologies, I should say. These are interesting memory technologies because these can potentially replace main memory, DRAM. There are also storage technologies that are interesting that I didn't put over here, but people are looking at, for example, storing data in terms of etching things into a glass. Not the way I would do it, of course, right? There are ways of doing it optically, for example. And people are looking at also storing data in DNA. This is called DNA storage. I think these are much longer term potentially, but there's a lot of work going on there. So materials are very interesting. Let's put it that way. Okay, so I will not talk more about this. We cover a lot of these in, let's say, later courses, seminar courses, etc. But if you're interested, you're welcome to take a look. I will mention one thing. Why am I telling you this? Because today, some technologies we take for granted were emerging technologies in the past. This thing, flash memory, for example, this is an area that we have worked on a lot in my group. We're still working on it. It was a very doubtful emerging technology for at least 2 decades. It was developed in 1980s or late 1970s by Toshiba. And nobody really understood the potential of it, let's say, until, I would say, in the mass market, Apple did it, right? They basically used this as storage for music initially, and then many, many other things later. And this happened, let's say, in early 2000s, actually even late 2000s. And then we figured out how to use this in our cell phones and in our laptops. So flash memory is really the state-of-the-art storage in all of our devices today, right? In the data centers also. So never underestimate the importance of an emerging technology and dismiss it. This was dismissed by many people. If you actually know how to take advantage of a technology, it's a painful road. It takes a lot of time, and you may not be successful, but these technologies can change the world. And I would argue that this is beneficial and useful mainly because of the flash memory. If we didn't have that much flash memory, we wouldn't be wasting a lot of storage, let's say, or we wouldn't be having a lot of storage to begin with. Okay, so again, I don't have time, but flash memory is also interesting. And if you, this is a memory technology that has interesting trade-offs. Many things don't work initially. So if you look at the bits that are stored in the flash chips, a lot of them are wrong. So what makes it work is really heavy work that is done by the controller. There's a controller that sits, it's called an SSD controller, that has a DRAM inside, that has its own separate DRAM. And that does a lot of work to actually make sure that the data stored over here is not wrong. Again, this may sound mysterious, but this is the truth. And how do you make it work is a key issue. And that's why people write articles like this. Okay. Okay, so I will leave it at that. You can, again, watch a lot of lectures. And also, if you want to learn more, you can attend future courses. And we also have an SSD course that's led by Mohammed over there and Rakesh, where we cover a lot of flash memory issues if you're interested. Okay, so I will also mention that we'll talk about processing in memory, hopefully in the last lecture. We'll have time, but if you're interested, you can take a look at it earlier. We also have a PIM course. I will skip that. Okay, now let's go into memory hierarchy. So this is actually related to memory technology. That's why I wanted to mention these different technologies and also processing in memory. That's also actually very interestingly dependent on memory technology, but it could be independent also, as we will perhaps see. But now let's jump into the memory hierarchy. In addition to enabling better systems like flash memory did or DRAM did, again, DRAM was an emerging technology in the 1960s. Also, I'm going to show you a slide later on. It emerged very quickly and it got rid of a lot of memory technologies from the field, some things that you don't see today. Flash memory wasn't able to completely get rid of disks, for example. Hard disks still have their place for the reason that I will show you soon. But DRAM got rid of a lot of old memory technologies in 1970 when it was first introduced. In addition to enabling much better systems, the disparity between these memory technologies and also requirements we have from the memory system require us to have memory hierarchies. And if you look at the memory hierarchy, you actually have different technologies, not completely, but in, different parts of it have different technologies. And it can have even more technologies. For example, some of the non-volatile memories can be on chip and replacing SRAM technology because it may be a good fit over there. And people have been proposing it. It has not happened yet, but it may happen soon. So these pictures I've shown you, basically today's systems have memory hierarchies, right? Cores have registers and then L1 caches, and then you have some L2 caches, and then you have some L3 caches, and then you have some DRAM, right? And there are controllers for all of these. We will see some cache controllers today and tomorrow. And you can see that some of these are explicitly described. Some of these are not explicitly shown in this, but there are caches in the cores. There are L2 caches over here. A lot of the regular structures are essentially caches on a chip. And Apple has a system level cache. That's essentially another cache shared by these different cores and accelerators. And this is another look at the memory hierarchy. SRAM, a lot of so if you look at the memory hierarchy on chip, it's a lot of SRAM. And then there's DRAM, which is also part of the memory hierarchy. And then there's storage, which is also part of the memory hierarchy. And we will connect how storage exactly is a part of the memory hierarchy when we talk about virtual memory later on. Okay, I could keep going and showing these things to you. But there was a time when SRAM caches were off chip. Today, we're not there anymore because we can put a lot of things on chip. Okay, so remember we discussed in the last lecture, what is ideal memory? Today we're going to try to approximate it by building a memory hierarchy. We're not going to be completely successful, but we're going to enable some trade-offs at least. So ideally, we want 0 access time and infinite capacity. We're going to look at especially this trade-off. We're not going to consider 0 cost, not yet, infinite bandwidth, 0 energy. But we should keep those in mind also. So if you want to get all of these at the same time, you have a problem at hand. It's very difficult, basically. Why? Basically, ideal memory's requirements oppose each other. Even if you look at the top 2 over here, access time, latency, and capacity, they're completely opposed to each other, as we have seen actually in the last lecture, right? That's why we built these smaller and smaller and smaller arrays as a building block and combine them in different ways, right? We didn't build a large monolithic array. Large monolithic array is large, but slow, essentially. So we divide it into pieces. Once you divide into pieces, you add additional latency actually to it as well, and cost. Okay, so basically bigger is slower, faster is more expensive, and higher bandwidth is also more expensive if you want to add another dimension to this. Why bigger? If a memory is monolithically bigger, it takes longer to determine the location. Now you know why. Because you need to drive the word lines and you need to drive the bit lines, right? And if these interconnects are longer, which is needed to make the memory bigger, it takes longer time to drive the word lines and drive the bit lines, essentially. Okay. There's another way of making things bigger that is actually reducing the size of the bit cell. And once you reduce the size of the bit cell, you actually fundamentally reduce the, let's say, amount of charge you store in DRAM, and it becomes more difficult to sense. So more difficult in this case means it's become slower to sense as well. So basically, there's another aspect to this bigger. You can make a memory bigger by reducing the size of the cells, or you can make a memory bigger by having bigger arrays, right? And both of them actually make it slower. There's actually another aspect to this. By reducing the size of the cells, you fundamentally make the cell less reliable. And if you want to read it, you need to do error correction, for example, on top of it, and that makes it slower also. So regardless of however you cut it, however you try to make it bigger, there's a fundamental trade-off between capacity and latency, okay? I like explaining it from this perspective of the arrays, but if you reduce the size of the cells, you get to the same place. Faster is more expensive at the same time, and this is memory technology. We have SRAM is more expensive, as we have seen, right? You need at least 6 transistors for it. DRAM is less expensive. SSDs, disks, tapes, they're progressively less and less expensive. But they become slower and slower also. Fundamentally because of the technology, because of the way you read it. For example, with phase change memory, we discussed that, okay, we want to replace DRAM, but unfortunately, the fundamental way in which you read, you need to heat up the cell so that you can see the resistance of it. Higher bandwidth is also more expensive, and we've seen this already. If you need more banks, more ports, more channels, or higher frequency channels, or faster technology. And they're all more expensive, essentially. So we don't have an out, if you will. If someone that basically gives you a technology that's large and fast at the same time, this is either a breakthrough or they're wrong. And it's usually the latter. Okay, so let's take a look at this problem. We'll put some numbers over here. I'm going to show this in a table. But basically, these are different technologies over here. You can see that bigger is slower. So SRAM can be nanoseconds. Hard disks are milliseconds today. SSDs are microseconds, as you can see. And faster is more expensive. In today's numbers, SRAM is expensive. This is actually real money that you need to pay per megabyte. DRAM is much cheaper, as you can see. And phase change memory is slightly cheaper than DRAM because it may not be, let's say, mature in terms of manufacturing yet. But you can see flash memory is orders of magnitude cheaper than DRAM. And hard disks are actually cheaper than flash memory, but not that much cheaper. Okay, and other technologies have their place as well, but they're not put there because a lot of them are not mature yet. I put phase change memory over here because it exists, but take the numbers with a grain of salt. Even though they're somewhere between DRAM and flash memory, maybe they can be scaled better. So this is at the table view of the same thing. If you're interested, you can take a look. But I will also show you a new thing that we added over here, which is energy per access. There's another aspect, right? Today, energy is extremely important. Basically, this shows that bigger is slower, faster is more expensive. And this table shows that faster is also more energy efficient. So if you actually try to keep the data in SRAM and operate from SRAM as much as possible, this is also more energy efficient. Because once you go out, the interconnects actually become much worse. But take these numbers with a grain of salt because there are different assumptions in how you calculate the numbers. What really matters is this is picojoules. Maybe this is an order of magnitude worse, and this may be similar somewhat. And now you go into the nanojoule territory over here with SSDs, and then you go into the microjoule territory. This is to access 1 byte, right? So you can see that it becomes much more expensive to access 1 byte as you go to larger structures, if you will. Okay, this is the 2011 version. If you have time, you can compare it to it. And you can see that the values have scaled quite a bit. So in 2011, you can see that DRAM cost was less than $1 per megabyte. It scaled very well, let's say, in 12 years. That's a lot. Almost 3 orders of magnitude. Well, I guess 200x or something like that. Okay, so basically memory is scaling nicely, but there are issues also. Okay, so why do we have memory hierarchy? Because of what we just saw. We want both fast and large, but unfortunately we cannot achieve both with a single level of memory. So the idea of a memory hierarchy is very simple. Essentially, add heterogeneity, if you will. Or in other words, add multiple levels of storage that become progressively bigger and slower as the levels are farther from the processor, and ensure with some techniques that hopefully most of the data the processor needs is kept in the faster levels as much as possible. We're going to see that it's not going to be possible all the time, but if you actually keep at least some data over there, it's still better than not having a memory hierarchy, let's say. So basically, this is the simplistic picture that you have in our, let's say, chapter that I assigned. You have some caches that are small and fast, and you have main memory large and slow. And you can expand this basically. You can expand main, there's a backing store, which is SSDs and hard disks to main memory. And they're even larger and even slower, let's say. And then you can put energy over here also, right? So basically, it looks like this. You have some fast and small memory, and then you have large but slow memory as well. And whenever you use something, you move it from the large but slow memory, because everything is initially stored over there. You back up everything here also. Move what you use over here. And if you have good locality of reference, hopefully memory appears as fast as this one and as large as this one. You get the benefit of both worlds. But of course, this requires some management and also a good locality of reference. And then you can generalize the idea by adding more levels, right? Adding more levels doesn't change the fundamental idea. It just enables better trade-offs. And if you cannot put everything that you need over here, maybe you will be able to put it over here, right? Hope. We can always hope. Okay, so basically this is a fundamental trade-off. Fast memory is small, large memory is slow. And with memory hierarchy, we hopefully get the benefits of fast memory as well as large memory at the same time while avoiding the disadvantages as much as possible. Now, it's not just, of course, small and slow. Once you go from the fast memory, which is the fastest of which is the register file, actually the registers on the CPU, other microarchitectural registers can be considered memory also, depending on what you use it for. But at least register files exposed to the programmer, right? And then there are caches, and then there's main memory, and there's hard disk, and then we can add more. So there's a trade-off in terms of latency, cost, size, and bandwidth, right? So basically, as you go from left to right, latency increases, cost reduces, size increases, and bandwidth or throughput reduces, right? And energy, as we saw, increases also, right, as we go from left to right. So this is an example of memory hierarchy today. This, hopefully in the next lecture, I'm going to extend it to farther memory also. This is a single node. And also there's an SSD, etc. over here. But basically, L1 caches are on the order of tens of kilobytes. L2 caches are hundreds of kilobytes. And the latency is higher, as you can see. L3 caches are several megabytes. And then main memory is several gigabytes. Of course, you can add more channels to increase the capacity, as we have discussed, right? And then we'll put SSD in a later picture over here. But also in today's very large scale applications, because you cannot fit the application in a single node, you scale up to many nodes in a data center, for example, and you can access remote memories as well. So there's this is something that I will discuss hopefully in the next lecture very briefly again. We won't go into a lot of detail, but that's an example of memory hierarchy also. Memory hierarchy can expand beyond a single node, right? You can actually take the memory hierarchy of this and put some of the memory to some other node, some other computer, that one potentially, connect them in some way, right? Okay, so why does this work? This works because fundamentally, there's locality of reference. And locality of reference is essentially related to the fact that one's recent past is a very good predictor of their near future applied to programs. I'll apply to you at this point. So temporal locality, there are two types of locality, temporal and spatial. They can be combined also. So a temporal locality says if you just did something, it's very likely that you will do the same thing again soon. And this happens actually. There's a lot of temporal locality in the world, right? I'm lecturing, for example, for how many minutes, right? So I can predict that I'm going to keep lecturing for some time, right? Or since you're here today, there's a good chance that you will be here again and again regularly. And I know that very well, actually. I can recognize the faces, right? So temporal locality holds nicely here. Spatial locality is fundamentally different. It's in space. Essentially, the first one is in time, the other is in space. If you did something, it's very likely that you will do something similar or related in space, at least in this perspective. For example, every time I find you in this room, you're probably sitting close to the same people and in close by seats that you sat in the past, right? And that also holds, I think, in most of the cases. Some of you actually play random access, of course, which is fine also. So this doesn't always hold clearly, but due to some fundamental nature of things that we cannot completely explain in this particular case, perhaps, habits, let's say, that's still a very high level thing, right? There's some underlying explanation about human computation that happens that we don't quite know really, in my opinion. But this happens, let's say, right? So this happens in programs also. This is the memory locality, essentially. A typical program has a lot of locality in memory references. One of the major reasons is typical programs are composed of loops, and they keep operating on the same data over and over, or they keep operating on data that's close by to each other. And these are temporal and spatial locality, essentially. Temporal locality in this particular case, when applied to memory, means that a program tends to reference the same memory location many times and within a small window of time. Right? Okay, so that's good. Why does this happen? Because there's some variables, right? This is why we put registers in the von Neumann model, right? We put some registers next to the processor because there are some things, some variables that we reuse close by, and they capture the temporal locality. And if you go out a little bit longer time frame, there are some other variables that you reuse at a longer time frame. And if you actually go out in an even more longer time frame, there are some other variables you reuse. These are all temporal localities. So temporal locality has a temporal aspect to it, as you can see, right? It depends on the time window you look at. This time window can be very short. This time window can be very large. But even if it's very large, this is temporal locality. You may actually reference some variable every week. If you figure that out, you can exploit temporal locality, right? If you don't figure that out, probably you won't be able to cache it nicely in any of your structures because a week is a very long time, clearly. Okay, spatial locality is the idea that a program tends to reference nearby memory locations within a window of time. Most notable examples, we've seen actually a lot of these, instruction references, for example, right? Instruction references, because of the von Neumann model, they're sequential. You actually go sequentially in the instruction stream, unless there's a control flow operation. But control flow operations actually can put you back to a close by location in the instruction stream also, right? So basically, this is the reason why you get spatial locality in instruction references. And in memory, in data references, remember we talked about SIMD processing, an example. We often operate on arrays, vectors, or matrices. And these are sequential structures, right? These are sequentially laid out. And we wanted to actually make the stride one, meaning that the next memory address we touch using this instruction is going to be the next consecutive address in memory. That's essential spatial locality, right? We want that for other reasons, as we have discussed last time, right? In SIMD. So we actually want to increase the spatial locality in our systems also. But this is not always a function of what we want. This is also a function of what the program is doing and what the input set is, right? There are some cases where you may have a huge graph, and this graph, you cannot lay out the things that you're going to touch consecutively in consecutive locations in memory, right? Because you don't know what you're going to touch in this graph, right? Okay, so spatial locality and temporal locality both are functions of the programs in the end. Okay, and this is what caches essentially exploit. Caches exploit temporal locality, and caches are a fundamental part of the memory hierarchy. In fact, you can view any memory as a cache, if you will. But basically, they store recently accessed data in an automatically managed fast memory. And this is called a cache today. It's basically fast memory that's automatically managed transparently to the programmer, usually. And the anticipation is that same memory location will be accessed again soon. So this is a temporal locality principle, as we discussed, right? Recently accessed data will be again accessed in the near future. And this is what Morris Wilks had in mind. This is one of the earlier cache papers, as you can see. I'll just read it over here. the use is discussed of a fast core memory of, say, 32,000 words. That sounds very ridiculous today, right? We have much bigger memories today. As a slave to a slower core memory of, say, 1 million words, in such a way that in practical cases, the effective access time is nearer that of the fast memory than that of the slow memory. So it's beautifully expressed, as you can see, right? So what is core memory? I'll show you a picture of core memory soon. That's the memory technology of the day. So that's temporal locality, and we do that today. Spatial locality is essentially what we discussed, but the idea to exploit spatial locality in a cache is to store data in addresses adjacent to the recently accessed one in automatically managed fast memory. Basically, whenever you're storing data, you don't take just the data that you are accessing, but just take the data within the vicinity also of that data. So the way it's done in hardware caches is to logically divide memory into equal size blocks, because this makes management easier in hardware, equal size. And we fetch to cache the access block in its entirety. So we're going to talk about this a lot in today's lecture, how we actually do this, how we actually build the structure. It's not that difficult, as you will see. So the anticipation, though, is that nearby memory locations to that memory location that you're accessing right now will be accessed soon. And that's based on the spatial locality principle, right? Nearby data and memory will be accessed in the near future. And we know the reasons. We've discussed this earlier. And this is also what was implemented earlier. This is an early system that implemented cache, IBM 36085. This is not what the other papers actually discussed. IBM actually implemented this without, let's say, writing earlier papers saying that we're implementing it. They basically had a 16 kilobyte cache with 64 byte blocks, which is interesting, right? And if you're interested, you can read their paper. So my analogy to the memory hierarchy is this. So if you read books, then you may have a bookshelf, but bookshelf is too far, right? You cannot really read the book while the book is in bookshelf, right? If you can do that, that's great, and I'll applaud you. Let me know how you do it. But you need to bring the book somewhere, right, into your hand first. And this is what you're doing at this point. You're exploiting temporal locality principle. The book you're reading, you're going to continue reading that book for some time, hopefully, right? And once you're done, you're going to put it somewhere else. That somewhere else is probably the desk, or maybe the bookshelf again. Or maybe you hate the book and you send it to storage, or you start selling it somewhere, right? That's another. So basically, this is the analogy, I think. Book in your hand, desk, bookshelf, boxes at home, boxes in storage, and the hated book somewhere else. Hopefully, they're not computer architecture books. Okay, but recently used books essentially tend to stay on the desk or in your hand, but your hand doesn't have, let's say, large capacity, but it has fast access. As a result, you use your hand to really work on the things that you're working on. Of course, until the desk gets full, then you actually start putting things into the bookshelf potentially, right? So that's the temporal locality, I would say. And there are capacity issues over here. But this is a very nice example of a memory hierarchy, in my opinion. And then the question is, what is spatial locality? Well, spatial locality in this particular analogy is that adjacent books in the shelf may be needed around the same time, right? Because they may be on a particular topic. Let's say all of your computer architecture books are nicely organized together, such that, oh, I want to look at this topic in this book. You look at it, and then I want to look at this topic, same topic in the next book to see how they've described it. And then you look at this, and you're streaming through your computer architecture books, for example, right? Of course, this only works if you organize your data nicely, such that you can stream through it, right? If your computer architecture books are randomly located in your bookshelf, this is not going to work nicely. You won't have the spatial locality principle. You'll be randomly accessing things, even though logically the books are related to each other, right? Okay, so this indicates the importance of the data mapping, basically. You need to map your data in a manner that's, let's say, consistent with your access pattern. Or the mapping of your data determines what kind of access pattern you get to your bookshelf, right? Is it random or is it sequential in a single shelf, let's say? Okay, so we can keep the analogy going, but that's not the purpose of this lecture. Let's talk about how this works in a pipeline design, because we've talked about pipelining, and this actually imposes some other requirements. So memory hierarchy cannot be studied completely independently from the processor, because in the end, it serves the processor, right, in today's systems. And we've talked about caches, and we've talked about when we designed the pipeline, we said, oh, you have a load request, and we want to get it directly from memory, right? So, and we said that we're going to assume, let's say, magic memory, such that you get the data in one cycle. If you don't get it in one cycle, you need to stall, as we have discussed, until the cache response. This means that the cache needs to be tightly integrated into the pipeline. And ideally, you access in one cycle so that load-dependent operations do not stall, do not wait. Right? We know how to tolerate small latencies without order execution. So today, we don't have one-cycle caches. Today, we have actually 3-4 cycle L1 caches in general, because frequencies are very high also, right? But essentially, with a high-frequency pipeline, you have another constraint. You cannot make the cache arbitrarily large. But we want a large cache and also a high-frequency pipeline today, right? So this is another motivation for a memory hierarchy. And also, or cache hierarchy, if you will. Or this is another motivation of actually managing the L1 cache in a different way than other caches. So basically, we have cache hierarchies today. We don't just have a single cache on chip, because if you had a single cache on chip, the pipeline would stall a lot. Instead, we have a level 1 cache whose design decisions are primarily dictated by the frequency of the processor. So it's actually very small, 16, 32, if you're lucky, 128 kilobytes. It's actually very small, but reasonably fast. Hopefully one cycle, but usually not today. And then you have a level 2 cache, that's the next level, that is larger, but slower. Okay. Does that make sense? So I want to make sure this point is clear, because the way you manage the L1 cache, this is also going to diverge how we manage L1 cache and L2 cache and L3 cache today. Because L1 cache is really dictated by the CPU. You can, even in the pictures, you don't see L1 caches today. People say, oh, this is my core. It includes the L1 cache. Nobody talks about it, but it's there. L2 cache is out there. And in some cases, actually, L2 caches are being integrated into the core today also, but that's another discussion. I should also discuss manual versus automatic management, because this is also interesting. So manual means programmer needs to manage the cache, or which data needs to come to the cache, which data needs to move where. Automatic means hardware manages the data movement across levels transparently to the programmer. Today, we refer to the term cache primarily as an automatically managed hardware structure. We don't talk about manual managed. We call a manual managed cache as a scratchpad, for example, as we will see. So the reason is manual management is too painful for programmers on substantial programs. And people have figured this out based on experience. Old systems in the 1950s, for example, required manual management. There was core memory, which was faster. There was drum memory, which was slower. And programmer needed to manage what needs to go to the core memory. Or there was some small core memory, as Morris Wills discussed, and large core memory, and programmer needed to manage. This was too painful. It's still done in some embedded processors, although it's changing over there. You have on-chip scratchpad SRAM. In GPUs, you have some on-chip scratchpad SRAM. In some machine learning accelerators. So it still exists. When the programmer knows the application, for example, they can decide what should go into this another level of memory. The reason I don't call it a cache here is because this needs to expose a different address space to the programmer. Now, the programmer needs to see another address space so that they can say, move this data from main memory to the special memory on my chip, right? Okay, so we're going to talk about automatic management. Clearly, the huge advantage of automatic management is programmers' life is easier. They can get high performance without thinking about anything, hopefully. The average programmer, as a result, doesn't need to know about caches. You don't need to know how big the cache is, for example, or how it works to write a correct program. And you get performance improvement with these caches. But if you really want to take advantage of this cache hierarchy, you'd better do something about your program. And we will see that. And this requires restructuring your code such that it fits in the working set fits into your caches, for example. That's one example. Or rearranging your loops so that you have a good access pattern that can be exploited with the spatial locality exploitation mechanisms that are used in caches today. Okay, so I'll give you one example. Scratchpads exists. In fact, in a lot of NVIDIA GPUs today, some memory can be used as L1 cache or scratchpad. It's basically at the discretion of the programmer. Programmer can say, oh, I'm going to use this as scratchpad or some portion of it as scratchpad. And this is increasing, as you can see. This is the more recent NVIDIA chip, and it looks nice like this also. You can see that there's 256 kilobyte per streaming multiprocessor, can be used as L1 cache and scratchpad. And you can do the multiplication over here. I think that's close to, I don't know, 40 megabytes total, something like that. Yeah, you divide 144 by 4 and you get something like that, right? Less than 40 megabytes. And that's true for this thing that we have discussed, the wafer scale engine we've discussed also. We said that this is 18 gigabytes of one chip memory. This is essentially a scratchpad. So you saw this picture somewhat when we talked about SIMD accelerators, right? There's a SIMD unit over here. And essentially it has an SRAM, they call it memory. This is essentially scratchpad memory in each tile. And you can see that there are 4,500 tiles over here. And this scratchpad memory is managed by the programmer. And hopefully the programmer knows what they're doing. And there's no other way. You cannot manage this as a cache. It cannot be automatically managed over here. They basically say the programmer should know what they're doing and put the data that they're going to reuse a lot into this memory. Okay, and that's what amounts to 18 gigabytes total, the collection of all these memories across the tiles and across the many, many dies in the wafer. Okay, and this is increasing, as you can see. Now they have 40 gigabytes of scratchpad memory. Okay, let me give you the historical perspective before we delve into a little bit more detail. So this was the drum memory in 1950s, and this is the core memory. And people used to manage this core memory as a cache or programmer managed cache, the drum memory. And then later, this drum memory was not very good, so core memory replaced everything. And you can see the core memory. This is actually, you can see the word lines and the bit lines over here. And you can see the orientation of these magnets over here that store ones and zeros. So you can actually figure out what it's storing, but I'll let you figure that out. But for this thing that you cannot read over here, let me actually point out one thing. Yeah, some manufacturing things, but the introduction of the first semiconductor memory chips in the late 1960s, which initially created static random access memory, began to erode the market for core memory. This was the dominant memory at the time. The first successful dynamic random access memory, DRAM, the Intel 1103, followed in 1970. Its availability in quantity at 1 cent per bit marked the beginning of the end of core memory, and for core memory. So 1 cent per bit, you can translate it to 0.006 cents for, I think 0006 actually, cents per megabyte today. Okay, so let's talk about automatic management a little bit. So this is what also Morris Wilks had in mind. Basically, he says, by a slave memory, which is called cache memory today, I mean one which automatically accumulates to itself words that come from a slower main memory and keeps them available for subsequent use without it being necessary for the penalty of main memory access to be incurred again. Again, this is the fundamental principle, and it's beautiful also. But I will give you a historical aside also. Caching has been around for some time. That's not the earliest cache paper. The earliest cache paper that is hardware cache is this one, actually. I'll give you a picture that we're going to construct soon. So this is from that paper. And if you look at this cache, basically there's some data storage. So a cache needs to store some data, blocks essentially, that are being cached right now. And also some metadata that's needed to identify those blocks, what is needed to be cached. And that's the fundamental structure of a cache today. You have a tag store, metadata, and you have a data store. And when the processor needs to query the cache, it needs to send an address to the metadata store, which is the tag store. And if the metadata indicates that this address exists in the cache, then you can actually get the data out of the cache. If the metadata indicates that this address is not in the cache, then you have to go to main memory. But this is actually the fundamental structure that we're going to develop. But today we have actually a lot of caches. Before we go into the cache design, I want to go through some high-level analysis to discuss what actually dictates the design decisions. Because yes, you can construct the cache in some way, but then how do you actually make the design decision such that you have, let's say, 3 levels or 4 levels or n levels, right? What is the size of each level? What is the latency of each level? This is actually a very complicated part of the system, right? So one of the things that people do is this hierarchical latency analysis. This gives insight into things. Let's assume that a given memory hierarchy level I has intrinsic access time of Ti. So for example, for L1 cache, you have some intrinsic access time for the cache. And register file is actually also part of the memory hierarchy, but it's special because it's really managed by the compiler or a very motivated programmer, let's say, but usually the compiler today. Disk is also a part of the memory hierarchy today, but today it's managed by the system, as we will discuss with virtual memory. So don't forget those parts, but we're talking about this right now in hierarchical latency analysis. So each level over here, in this case, we have 3 levels of caching, at least. Main memory has some, is the last level. We're going to assume that everything exists in main memory in this analysis, which is not necessarily true. You can expand that analysis to other parts also, but for simplicity, we're going to assume everything exists in main memory. So a given memory hierarchy level I has intrinsic access time of Ti. But this is just the access time of that level. This you query that level and you get a hit or miss, basically meaning that the data is there or not there, and it takes TI amount of time for that level. Clearly, this depends on the size of that level, right, and the technology of that level. But the real perceived access time is longer than TI. So this large TI is longer than TI because whenever you send an access to some level, you have this intrinsic access time, and the accesses that hit in that level, that are found in that level, incur that intrinsic access time. But the accesses that are not found in that level need to go to the next level, right? That means that you incur some more time. So you can basically denote these different accesses with different things. So whenever you're looking for a given address, except for the outermost hierarchy level, which we assume everything exists, there's a chance that you hit at that level. And this chance is denoted by the hit rate of that level, HI, and the access time is equal to TI. And there's also a chance that you miss at that level because the data is not there. And this chance or probability is the miss rate, MI. And the access time is at that point, the intrinsic access time plus the perceived access time of the next level, because you need to go to the next level at that point. So hopefully, clearly, it should be the case that hits plus misses are equal to 1. That's essentially all of the accesses. You're never in a quantum state where you don't know what's going on, basically, let's say. But if you actually expand this equation, the perceived access time at level I is the hit rate of that level times the intrinsic access time of that level, plus the miss rate of that level times the intrinsic access time of that level, plus the perceived access time of the next level. Because now you need to go to the next level for accesses that miss. And if you actually use this equation to make this simpler, the perceived access time of level I is the intrinsic access time of that level, because every access needs to go through that intrinsic access time to figure out whether it's a hit or miss, plus the miss rate at that level times the perceived access time of that next level, okay? So we've already discussed this, right? HI and MI are defined to be the hit rate and miss rate of only the references that missed at level I-1, the previous level, essentially. Okay, so basically now we have a recursive latency equation, right? Which is interesting. And the goal is to achieve desired first level L1, let's say L1 cache, perceived access latency within some allowed cost. So you have some cost constraints and some other constraints, of course, like energy, power, etc. But your goal is to also get some reasonable access latency to the requests that are going to the first level. Because that's what in a processor-centric system, which we've been developing, that's what you care about, right? How fast am I going to get the data? How long am I going to wait? Ideally, 1 cycle, as we discussed, right? But we're not going to get that, as we will see soon. So what you really desire is, at any level, you would like to get the intrinsic access time of that level. Ideally, you should hit at any level, right? You present the access to some level, you should hit. Clearly, it's not going to happen, right? So as a result, we want to keep miss rate low as much as possible. But unfortunately, increasing capacity CI lowers the miss rate, which may be good, but this increases the intrinsic access latency also, TI. So that's the trade-off, right? You can lower the miss rate by doing smarter cache management, which we're going to talk about today and next week, probably next week a lot. You can do replacement, anticipate what you don't need, for example. You can do prefetching, anticipate what you will need. There are a lot of management mechanisms that you can use, actually, to reduce the miss rate. But this is one of the reasons why we also have hierarchies, because you increase the intrinsic access latency if you increase capacity. So it makes sense to actually have another level of hierarchy whose intrinsic access latency is higher, but you don't access as often, okay? So we also want to keep the perceived access latency of the next level low as much as possible. So here, again, you run into a trade-off. You can have faster outer hierarchy levels, but again, cost may increase. So as a result, we introduce intermediate hierarchy levels. That's one of the reasons why we keep introducing these intermediate hierarchy levels. Okay, so let me give you an example of these equations. Why am I telling you this? Because there's something interesting that comes up over here also. Pentium 4 was a state-of-the-art processor of its time, and it had this huge L2 cache for its time, 1 megabytes, as you can see. It has this L1 cache, 16 kilobytes only. Even though the technology allowed them to actually have much bigger caches, they did not. Because their frequency was high, they could not afford an L1 cache that's larger. And we're going to talk about what 8-way means soon. And then there's a trace cache, which is essentially an instruction cache for them. And this is the huge L2 cache, as you can see at the time. And you can probably see the L1 cache is over here, one of those. Okay, so let's take a look at an example. This is the 90 nanometer version of it. It was running at 3.6 gigahertz. Doesn't matter. Let's take a look at these values over here. So they designed an L1 data cache that is 16 kilobytes, and the intrinsic access time was 4 cycles for integer accesses. For floating point, it was larger access, so they need more cycles, but we're not going to talk about floating point here. For L2 data cache, capacity was larger, as you can see, and the intrinsic access time was 18 cycles. And for main memory, we're going to assume average access latency of 15 nanoseconds and 180 cycles. So T3 is intrinsic access time, and we're going to assume that you don't miss in main memory. You're lucky. Everything fits in main memory. That doesn't always happen. So notice several things over here. The best case latency is not 1. For this real process, it's 4 cycles. Why? Because the frequency is very high, 3.6 gigahertz. It's still quite high, actually, compared to some systems today. We're talking about 1999. And the worst case access latencies are actually into 500 plus cycles, even more, but we're not going to bother with the worst case latency over here. We're going to assume this is the average latency. So let's look at how the perceived access time changes at the L1 level based on different values of miss rate. So for example, if the miss rate from the L1 cache is 10% and miss rate from the L2 cache is 10%, by doing the hierarchical latency analysis, you will get this. So the perceived access time at the L1 cache level is 7.6. How do I get this? Let's do the outer. You start from the outer side, right? Which is, what is the perceived access latency, access time of, yeah, let me go back to this equation. Yeah, actually, yeah. So let's do this. So essentially, you get, for every access, you get 4 cycles, right? You start with 4 cycles. 10% of them miss in the first level. They go to the second level, right? For 10% of them, you actually get 18 cycles, right? That gives you 1.8 extra. But 10% of them also miss in the next level. For them, you get I believe 18 cycles, right? 180 cycles. So if you do the multiplication, if you do the hierarchical latency analysis, the perceived access time of the second level is 36, and the first level is 7.6. Does that make sense? So it's essentially 4 plus 0.1 times 18 plus 0.01 times 180. Okay? Because only 1% of the accesses actually go to main memory, because 10% miss in the first level, and out of the 10% that miss, only 10% miss in the second level. Okay, so that's the idea. So 7.6 is still high, as you can see, compared to 4 cycles. So 10% miss rate, which one could argue is quite good, puts you to 7.6 cycle perceived access latency at the L1 level. That doesn't sound good. So let's take a look at another example that's much better. The miss rate is only 1% at the first level and 1% in the second level. You do the same calculations. You get closer to 4 cycles, as you can see, right? 4.2 cycles perceived access latency at the L1 level. But this requires you to hit 99% of your accesses to hit in the first level. And out of those accesses that go to the second level, 99% of those accesses to also hit in the next level, right? That's not easy also. So let's take a look at another interesting case. Let's assume that 5% of your accesses miss in the first level. And out of those accesses, 1% of the accesses miss in the second level. Now, if you do the equation, you get a perceived access latency of 5 cycles, which is maybe not bad, right? So you get 95% of your accesses hit in the first level. And out of the remaining accesses, you get only 1% miss in the second level. Now, this doesn't usually work that way, but it could happen. This could also happen. Your data set fits, for example, mostly in the second level cache, but first level cache is not very effective. That's okay. But let's take a look at another case where 99% of your accesses hit in the first level, 1% misses, which means that only 1% goes to the second level. Out of 1%, 50% may miss in the second level. And you get still an okay perceived access latency compared to the previous one. So this shows you that it really depends on what hits in the level. So there's a filtering effect that's going on, basically. A 5% miss rate over here, so a 1% miss rate over here is not the same thing as a 1% miss rate on the second level, because second level sees the filtered requests from the first level, right? If you actually have a very good hit rate in the first level, second level becomes less important, if you will. Does that make sense? So that's the major reason why we go through this analysis, essentially. So if your first level is very good, second level may be leaky, if you will, 50% hit rate. Okay, keep this in mind. Okay, so I think this is a great place to take a break until 15:25, and then we're going to talk about essentially construct caches. Yeah.
This is what we generates all control signals.
Exactly. Activate, recharge, read, all of those that we discussed.
Okay.
Yeah.
And then there must be quite a huge like control bus.
Exactly. Yeah. Yeah. Command bus. It's called the command bus. Yeah. Okay, I think we can get started. Before we go further, I want to bring up some picture over here that we looked at, because one question was asked earlier as to, okay, you have a hierarchy like this, and there are a lot of design decisions, right? How do you design the L1 cache, L2 cache, L3 cache? Are they designed using the same technology today? Today, most of these are SRAM, yes. But that said, the optimizations that are done at the circuit level are different for different caches. Because L1 cache is very much, again, goal is to have low latency. Capacity is not as important because you cannot fit in a lot of capacity anyway within a given amount of latency. You optimize it for latency in general so that the processor gets the data quickly. Whereas L3 cache, you already have many nanoseconds to access this anyway, so it's optimized more for capacity. Meaning you use different types of SRAM potentially, different types of cells, different types of circuit optimizations to maximize the capacity as much as possible at the L3 cache. So even though these technologies are SRAM, there are also different kinds of SRAM. Don't forget that. There are also different ways of optimizing the SRAM also. And there are also architectural decisions that are different, which we will talk about later on. The architectural decisions that you make in the L1 cache is not going to be the same as the architectural decisions that you make in the L3 cache. And then there's another question. Assuming that you access something in main memory, where do you bring the data, right? Do you bring the data that you access to all of the caches or to some of the caches? If it's some of the caches, which caches, right? These are all good questions. They're architectural design questions. We're going to tackle some of these, but we're not going to go into, of course, every possible design decision. There are lots of design decisions in this hierarchy. And we will see in some cases, and these actually affect the performance that you get. Clearly, these affect the hit rate that you get as well, and also the data moment that you incur in the hierarchy. Okay, and then another question was, how do you handle writes and reads? That's another question. Where do you write the data? Do you write it only to one cache, or do you write it to the entire level? We're going to discuss that as well. So keep that for now. Today, we're going to build a basic cache, and then we're going to go into some of these design decisions. But again, we're not going to be able to cover all of the design decisions. Okay, so let's move on. So let's design this basic cache that we wanted to get to. So let me redefine what a cache is essentially. Essentially, a cache is any structure that memoizes used or produced data. This is the most general definition that I could come up with. I don't think this exists exactly in any book, but this is really what a cache is, generally. And the goal is to avoid repeating the long latency operations required to reproduce or fetch the data from scratch. Right? You may not need to access from somewhere. You may actually produce that data using some computation and you store it into the cache, right? And then you actually fetch it. Instead of reproducing it again, you get it from memory. That's one potential use of a cache. A web cache, for example. The caches are used in many, many systems. In operating systems, for example, or in browsers, you have a web cache. Essentially, what you do is whenever you access some web pages, those pages get cached in some software structures in the browser, which clearly are realized in a disk or main memory in the end. And the browser manages this cache, right? It can cache some web pages that you recently visited. And the design of this web cache is clearly a little bit different from what we're going to design soon, because this is not a hardware cache, right? This actually is a software cache. You use software data structures. Eventually, they get implemented in hardware caches potentially, right? They get stored over there, of course. But there's a lot more flexibility in this kind of cache, right? And later, we're going to see prefetching. Some of the browsers do prefetching. They anticipate which links you may click, and they may actually prefetch some of those links, right? So you can actually do a lot of things at the software level also. In a distributed system, you see actually concepts of caching, software caching a lot. There's a program called memcached, for example. It's essentially doing caching in a distributed system. Okay, But in the processor design context, a cache is essentially an automatically managed memory structure. And that's the context we're going to look at. For example, we're going to memorize in fast SRAM the most frequently or recently accessed DRAM memory locations to avoid repeatedly paying for the DRAM access latency. Right? That's what we're going to see most. So this is the conceptual picture in the book chapter that I suggested that you take a look at. Essentially, in a cache, you have a limited number of cache blocks you can keep. And we're going to talk about hardware only at this point. You can actually generalize it to software. Flexibility increases in software. The blocks don't need to be of equal size, for example. Data structures don't need to be, let's say, simple, like what we're going to see. And then this is essentially the data that you store. A cache block conceptually stores the data and the metadata, actually. But usually when we refer to cache block, we talk about the data. But don't forget that there's metadata that needs to be associated with the data so that we can identify what that is, right? What is stored there. And this encompasses information about the cache block, most importantly, the address of the cache block. That's how you would figure out whether the address is in the cache or not. But also other information, as we will see. We will keep adding information to this. For example, have you written to this cache block? Have you accessed this cache block recently? This information is useful for managing the cache and the cache hierarchy, right? Have you accessed this block recently? May give you an indication of whether or not you should really keep this block in the cache when there are some other blocks contending for the cache, right? And you don't have enough cache space to keep everything, right? So we're going to see that this metadata store can actually grow. But you need this data and metadata. We're going to talk about the logical organization of a cache. And one key question in this logical organization is, how do you map the chunks of the main memory address space to blocks in the cache? So if you think about main memory has a physical address space. And essentially what we do is we divide it into chunks of cache blocks. And then the question is, you have a number of chunks. As you can see over here, we have 8 gigabytes of main memory. Each chunk is 64 bytes, equally sized as cache blocks. So you have many, many chunks. You can do the division of how many potential chunks or potential blocks you have. Then the question is, how do you do the mapping? Which location in cache can a given main memory chunk be placed in? And this is the first fundamental decision, one of the first fundamental decisions you make in the cache design. So let's take a look at 3 major choices. So I'm showing you over here a fully associative cache, which is the most flexible. Basically, any given chunk. And we also have a toy cache over here, as you can see. 4 cache blocks. You can cache 4 of these chunks in memory. So memory is 8 gigabytes. Each chunk is 64 bytes. Cache is very small, as you can see. At most, you can have 4 64-byte chunks or blocks. Now, fully associative cache is a cache where any chunk in memory can be mapped to any cache block. So it's very flexible. Of course, flexibility comes at a cost. You need to search the cache to figure out where the chunk is. So we actually are going to have 4 comparators for this one. Right? Direct map is the most inflexible. This basically says a given chunk can be mapped to only one location in the cache block. And this is determined based on some function that's applied to the address of the chunk. We will see that function is going to be simple, but you can actually make it arbitrarily complex as well. So this chunk may potentially map to this cache block, 0, let's say, but some other chunk based on its address can only map to this cache block. Right? So you don't have flexibility. And this is going to lead to what we will call conflict misses in the cache. Because, well, you can have conflict. Actually, you're not going to have conflict misses because of the definition of conflict misses later on. But this is going to, if 2 chunks can only go to the same location, you cannot keep those 2 chunks at the same time in the cache. Right? Even though you may have actually a space in the cache, right? As we will see. But this is much simpler, as we will see. Set associative is somewhere in the middle, basically. A given chunk can be mapped to a set of locations, set of cache blocks in the cache, a limited set. It could be 2 in this case, as you can see. But this is a toy cache. Okay, does that make sense? So we're going to see how these are actually realized in hardware, starting with a direct map cache, and then building a 2-way associative, and then 4-way associative, and the fully associative cache. And again, we're going to see a toy example. Okay, let me give you some basics in terms of like what we discuss in terms of terminology, and also some design decisions that we will discuss initially. So block, it's also called a line, is essentially the unit of storage in the cache. Memory is logically divided into blocks that map to potential locations in the cache. I called them chunks earlier, but we're going to transition to blocks. Unfortunately, there's no established terminology in terms of memory. In terms of caches, it's also blocks versus lines, and you see both in the literature. Even in the same book or same paper, you may actually see block and line interchangeably used. But essentially, you divide memory into blocks that map to potential locations in the cache. And we store those blocks in the cache in some way, as we will see. When you get a reference, when the processor actually references a block, a memory address, we call it a hit if the block is in the cache. And we use the cache data instead of accessing memory. Of course, this requires a mechanism to query the cache. You take the address of the block and you check whether it's in the cache, right? This is where the metadata comes in. And if that metadata says the block is not in the cache, you need to bring the block into the cache, basically. So clearly, when you bring the block into the cache, you may need to evict some other block, right? Depending on where you can bring the block and also what else is there in the cache. And eviction may require writing the block back to the next level or to memory if it's dirty. If it's not dirty, if the data value, dirty meaning if it's modified in the cache, because somebody has written to it. But if it's not actually modified, and it's the value that the block has is consistent with the other levels and main memory, then you just drop it, basically. You just make space in the cache for the incoming block. Okay, so there are important cache design decisions. We're going to look at these today and tomorrow. Placement is what we're going to cover today, where and how to place and find a block in the cache. Replacement is what data to remove to make room in the cache for an incoming block. Granularity of management, do you have large blocks, small blocks? Do you divide the block into sub-blocks? We will see the ideas and benefits of this. Write policy, what do you do about writes? Whenever you have a store, for example, or writes. Write is more general than a store because some levels of the cache hierarchy don't get exposed to the store instructions necessarily. They may actually have a block that's modified coming from an earlier level, right? That's essentially a write into the cache also. How do you deal with writes versus reads? And instructions and data, do we treat them separately? So there are actually many, many other design decisions also. But some of the interesting ones that fit in the slide are here. And these are relatively simple ones. Now let's take a look at how we build the cache. So essentially, we have an address that's given to us. This is the address of the block or byte that you want in the block. I'm going to treat it as byte that you want in the block, because that's more general. And you use this address to index into the data store over here, and then the tag store. Tag store answers the question, is the address that I'm looking for in the cache? And it gives a signal saying yes or no, hit or miss, essentially. And also has some bookkeeping information as we discussed, and we're going to add more to it. Data store essentially stores memory blocks. Data store is simple, just memory blocks, right? And if it's a hit, it gives data. If it's a miss, then it may give something, but you should not trust it, right? Okay. So cache hit rate, I'm going to talk about some metrics, but to foreshadow something quickly, cache hit rate, we've already kind of defined it. It's the number of hits divided by number of hits plus misses, or number of hits divided by number of accesses to the cache. And then we discussed average memory access time earlier. Essentially, it's hit rate time hit latency plus miss rate time miss latency. And this is hierarchical because miss latency is dependent on the next level, right? But something that you should think about starting right now is, I'm not going to answer it right now. Maybe I'll answer it, but you may think about why. Reducing average memory access time, is it always beneficial for performance? You may think yes, but today's processors are so complicated and memory hierarchies are so complicated that this does not take into account the cost of a cache miss. So it actually doesn't necessarily correlate perfectly with performance. And we will see that later on. Okay, so this is just to get you thinking. Now let's talk about a basic hardware cache design. We'll start with a basic cache design. Then we will examine a multitude of ideas to make it higher performance in general, better. But we're going to also look at some trade-offs, like what do you do in the L2 cache, L3 cache, L1 cache, for example. So as I said, main memory is logically divided into fixed size chunks, blocks. Why fixed size? Because it's easier to manage the cache, basically. People have proposed variable size blocks, and it becomes a mess, basically, in hardware. This doesn't mean that it's not doable. It's just much higher complexity. It's so high complexity that no one today does it, as far as we know. Cache can house only a limited number of blocks. That's why it's a cache, right? And this is a picture that I showed you earlier. So each block address maps to a potential location in the cache determined by the index bits in the address. So we're going to divide the address of a block into index bits and the tag bits. And we use these index bits to index into the tag and data stores, like I showed you earlier. So if you get an 8-bit address, I'm going to work with 8-bit addresses. You have 3 bits to designate the byte and block. Now this should, if you just look at this address, if you have 3 bits to designate the byte and block, that means that you have 8 bytes in block, right? Okay, hopefully that's true. Okay, that's what we are going to assume. And these index bits specify how you the locations in the tag and data store. So you basically chop off these bits, and this gives you the block address. Block address is really 5 bits over here. If you want to figure out what byte you're going to access in the block, you need these 3 bits also. So this is what I mean by a block address. Each block address is divided into index bits. Index bits are bits that you use to index the data store and the tag store. And then the tag bits are used to compare what's stored in the tag store to these bits so that you can determine whether this address exists. So I'm going to show you an example. So on a cache access, you first index into the tag and data stores with index bits in the address. So you get some essentially a tag value over there. And then there's a valid bit in the tag store that has to be there to say that, oh, this tag store entry is valid because somebody actually placed something here, okay? It has to be valid for you to get a hit. But that's not enough for you to get a hit. Then you need to compare the tag bits of the address that you're accessing with the address bits, tag bits in the address with the stored tag in the tag store. So a tag store indicates a tag saying that in this index, I'm storing this address with this tag. So we know the index because we've indexed in that location, right? And then the tag that I'm storing is these particular 2 bits. And if these particular 2 bits match the 2 bits that are using to query the cache with, at least the tag bits, then it's a cache hit, right? So essentially, if the stored tag is valid and matches the tag of the block, then the block is in the cache. That's a cache hit. If it's not, if any of these do not match, 2 and 3, if it's not valid or the tag comparison doesn't succeed, it's not equal, that means that there's some other block in the cache, right? Assuming the valid bit is 1 set, then it's a cache miss. Okay? Hopefully this makes sense. Now we're going to take a look at a direct map cache and see how it's constructed. Remember, a direct map cache, a given main memory block can be placed in only one possible location in the cache. Okay, so we're going to have a toy memory, 256 byte memory, which is small, as you can see. And we have a huge cache comparatively, 64 byte cache. And each cache block is 8 bytes. So it's essentially going to correspond to this address organization with direct map caches. Okay, let's take a look at this direct map cache. So this is our toy memory. We have 256 bytes in memory. We're assuming 8 byte blocks. So in total, we have 32 blocks in memory. So you can think of main memory, physical main memory, as looking like this, right? This is 32 blocks, complete. And these are the block addresses. Remember, even though to address a byte addressable 256 byte memory, I need 8 bits, right? But I'm showing you only 5 bits over here because these are the block addresses. The remaining 3 bits are specify which byte in block we have. But in the cache, we are storing 8 byte blocks. So we need those 3 bits only if we hit in the cache, clearly, right? Okay, so these are the blocks. So these are special because we've divided in a direct map cache. These map to the same location, index 0. Okay, let's assume a cache of 64 bytes, and you have 8 blocks, right? This is direct map. A block can go to only one location. So this is actually what our cache looks like. We have a tag store, 8 entries, indices 0 through 7. And then we have a data store, 8 entries also, indices 0 through 7. Data store stores the 8 bytes that may be in the cache corresponding to a block that's at index 0, and that's index 0 and specified by the tag that's stored here, assuming it's valid. That's how you can, now you can actually figure out how we index the cache, right? So in the tag store, we have a valid bit and we have tag bits. When we put some data into the cache, we essentially, when we put some block into the cache, we basically index the cache using the index bits, which is the 3 bits over here, and then set the valid bit, and then set the tag bits appropriately, 0, 1, assuming it's that block, and then write the data that we fetch from memory in the corresponding data store index, okay? Well, in this case, it's 0, 0, 0, so it should be actually written over here, I should say, right? The data at index 1, 1, 1, which means that this block can be written at index 1, 1, 1, which is 7. Okay, so basically, we divide our address, as we discussed earlier, into bytes in block. That's 3 bits over here because we have 8 bytes in a block. Log 2 to the 8 is 3. And then we have 8 indices, 8 potential locations that is determined by these index bits. That's 3 bits also. Again, log 2 to the 8 is 3. And then the remaining bits are tag. So these bits in the address specify which block or which location in the cache that a memory block can map to. Okay. So whenever we get an address, we use the index bits to index into the tag store as well as the data store. And we know how to do this, right? This is essentially a memory structure. We built these memories earlier. You use the address, 3 bits. This is essentially the address that you supply to memory. And you have an address decoder that tells you where it is located. If this is 0, 0, 0, then the address decoder activates this word line, right? And also this concurrently. We're doing that concurrently right now. And then we get, let's assume that this is 0, 0, 0. We basically get the tag store entry, valid and tag bits at address 0, 0, 0 in this tag store. And we also get the data corresponding to it at address 0, 0, 0. But now we're not done because we need to check the valid bit. Is it valid? We look at the valid bit in that entry. If it's valid, that's good. But when we're not done yet, we also need to check whether the tag matches, right? If the tag is equal to the tag that's stored over here, then it's a hit, okay? So you index into the cache, you get the valid and tag bits at that location index. It's called a set, as we will see soon. It's a set with only 1 block in this case. And then we check the valid bits and the tag bits. If it's valid and the tag bit matches the tag that we're, the tag bits in the address that we're accessing, that means that this block is already in the cache. It's a hit. Now, that means that we can make use of the data that we already also got by indexing the data store concurrently. And then we can use the byte in block to decide which byte we actually use, right? That makes sense, hopefully. You get 8 bytes. Byte in block actually multiplexes out the byte that you need. If you may need 2 bytes, you may need 4 bytes, you may need all 8 bytes, depending on your load instruction at the L1 level, right? It could be load byte, load word, load half word, etc., load double word. So essentially, this multiplexer is not that important, but don't forget that it exists around the cache, essentially. Okay, so hopefully that's clear. So as you can see, blocks with the same index contend for the same location. So these green blocks over here are potential blocks that go to the same location because they all have the index 0, 0, 0, right? So there are 4 possible locations, 4 possible blocks in memory that can go to the same location in cache. This is a small toy memory. In a real memory, this could be actually much larger. You may have 4 million possible blocks in main memory that actually map to the same location in the cache. And this poses a problem. This is why this direct map cache is not necessarily good, because if you need to store both block 0 and block, what is this, 8, right? At the same time in the cache, because it may happen that you're accessing both of them concurrently in your program for whatever reason. Unfortunately, you cannot store both because they map to the same index in the cache. And this is called a conflict miss, essentially. And this is why we need a little bit more flexibility in the design of the cache. This is the most rigid design. A given block can go into only a single possible location in the cache, right? There's no other location. If the index is 0, 0, 0, you go only over here. The next one, sorry, you cannot access there because that's not the indexing mechanism of the cache. there is a predetermined set of blocks that can be stored in index 001, and you know what those are. Those blocks with index bits corresponding to 001, right? Essentially, the blocks that are following these green blocks, and there are 4 of them. Okay? Any questions? So once you understood this, you now actually can build this cache, right? You know how to build this. This is the memory structure. Remember, we had a memory structure that had 4 locations and 3 bits each. Well, now we have 8 locations, and in the data store we have 8 bytes each. Okay, in the tag store, now you can calculate. We have actually 8 locations with 3 bits each. Not too bad. So that picture that we actually constructed, you just need to double it, let's say, right? So tag store is much smaller than data store. That also you can see over here right now. But we're going to make it bigger to get rid of this flexibility or reduce the flexibility, increase the flexibility, get rid of the inflexibility or reduce the inflexibility. Okay, so essentially, what's the problem? In a direct map cache, 2 blocks in memory that map to the same index in the cache cannot be present in the cache at the same time. Right, that's what I said earlier, because one index can store only one entry, one possible block. And this can lead to 0% hit rate if more than one block is accessed in an interleaved manner that map to the same index. If more than one block that are accessed in interleaved manner map to the same index. Let's take a look at an example. Assume addresses A and B have the same index bits, but different tag bits. These are addresses 0 and 8, for example, in the previous picture. And you access them like this. And these are the only things that you access, let's say, in your program. And this is the way you access them. You need to access something in block A, and then something in block B, and then something in block A, and something in block B, something in block A, something in block B. And you keep doing this forever. Even though you have this beautiful 8-entry cache, you get a 0% hit rate, right? Why? Because you're causing conflict misses. Why? Because your cache is inflexible to accommodate 2 things that map to the same index. That's the idea. So that's why we introduced some more flexibility. This is called set associativity, and we're going to see the reason why it's called associativity. We introduced flexibility to reduce these conflict misses. So the problem is addresses n and n plus 8 always conflict in this direct map cache in our toy example. And if you go back to this picture, essentially this is n, where n is 0. This is 8. This is 16. This is 24. Here, n is 1. This is 9. This is 17. This is 25. And you can do this. Basically, all of those equivalence classes map to the same index or same set. I'm going to introduce the set right now. So the simple idea is to enable blocks with the same index to map to more than one cache location. That's the simple idea. For example, I like thinking of it pictorially also. Instead of having one column of 8 blocks that you can store, why not have 2 columns of 4 blocks? What does this mean? This means that this is the cache that we had. We have one, if you look at just the tag store, we have 1 column of 8 blocks, right? Data store is also, essentially data store is a mirror of a tag store. You have 1 column of 8 blocks. Basically, you can store only one thing in a given index. Why not have 2 columns of 4 blocks each or 4 sets each? Which would look like this, essentially. So basically, in a given index, have the flexibility to store 2 things as opposed to 1 thing as before. So rethink the organization of your cache a little bit, basically. That's the idea. So this is a 2-way set associative cache. Blocks with the same index now can map to 2 possible locations. So this block with now, of course, because we have only 4 possible indices, because we actually rethought the organization of our cache, index bits reduced to 2 because there are only 4 possible indices that you have. So blocks with index bits 0, 0 map to these 2 possible places. But now you can have address n over here and address n plus 8 over here. And both of them can be present in the cache because we allowed for that flexibility in a given index without changing the size of the cache. The size of the cache is still 8 blocks, but we kind of looked again at how it's organized. That's the idea. Is this clear? So this thing, I don't know why it's moving, but well, okay, we can construct it. It's essentially the same thing that we saw over here. This is called a set. This is basically blocks that have the same index. They're called a set. It's a set of blocks that can be can be in the cache with the same index. That's the idea. Before, a set consisted of only one block, which is the direct map cache, right? And we had 8 sets. Now we have 4 sets, but each of them can contain 2 blocks. That's the idea. Now, okay, but the tag bits increased because you need to still uniquely identify addresses that are in your cache. So how do you do that? Well, the reading circuitry, the hit-miss determination circuitry became more complex. Why? Because now we need to index into the cache. Once we index into the cache, we have 2 possible things in the cache. And we have 2 possible blocks, as you can see over here. You have 1 val bit for each, because these really denote 2 distinct blocks, potentially. And you need to check both of them to determine whether you hit in the cache or miss in the cache, right? So if your address is, for example, all zeros over here, you index the cache, you get the valid and tag bits for this way, this is called a way, and you get the valid and tag bits for this way also. This is 2-way, right? The 0th way and the first way. And then you check whether each of them is valid. And if any of them is valid, you check whether the tag matches. Now, if any of them is valid and the tag matches, that's the block you're looking for. So there's logic to determine whether it's a hit. And there's a logic that says if it's a hit, which way it's a hit on. Is it way 0 and way 1? If you're hitting on both ways, you're doing something wrong in your cache. You should not store the same data in the same 2 locations clearly, right? That cause other problems that we will see. If you're hitting on none, well, that is not necessarily wrong. It's just your cache doesn't have the data, right? But basically, here's another mux that we introduce. This mux basically says it's a hit in the cache, it's in way 0 or way 1. And this is the data. This mux gives you the 8 bytes. And then you have the mux to multiplex out the bytes that you need in the block. Okay. Okay, so that's beautiful, as you can see. Why is it called associative? Within a set, we have associative memory. We've actually seen this, right? If you remember, we talked about content addressable memory in the reorder buffer in an earlier lecture. This is content addressable memory. Part of the address is in the content. Why? Because we're doing tag matching, right? And, well, it's associative also. Actually, that was true earlier as well with the tag, but it becomes more interesting over here because you're really searching. You have 2 possible locations that a block can be in once you get the data or the stuff that's stored in the tag store, and you search across them. Essentially, you're comparing the tag that you're accessing, part of the address, to the tag that's stored in way 0 and tag that's stored in way 1. And then you determine which one's the right place where data is stored. This is associative memory, essentially. And that's why it's called set associativity. Okay, so the big benefit is this accommodates conflicts better, as you can see. Now, if everything you're doing is accessing A and B, where A and B have the same index, you get 100% hit rate, clearly. That's great. Well, ignore the filling of the cache, of course, right? You need to fill the cache to begin. But of course, this comes at a cost, and the cost is hardware cost. You can see that we added, you need to do comparisons concurrently. So you need to have another comparator. We had only one comparator in the previous case. I need to do this concurrently, and the hit-miss determination complex logic becomes a little bit more complicated, clearly. And then you need to have another multiplexer over here, as you can see. And also a larger tag store. Right. Now, each of your tags is 3 bits, as opposed to 2 bits earlier. Okay? Make sense? Okay, so this is nice, but we can say the same thing. Okay, AB, there's nothing special about AB. What about we access ABC? Or let's actually make it even more dramatic, ABCD. I'm accessing ABCD, 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 ABCD. I still get a 0% hit rate, right? That doesn't sound good. So what do? Now you know the trick. Make this 4-way associative with this small cache still. Now, instead of having 2 columns of 4 blocks, have 4 columns of 2 blocks each. So you have only 1 index bit right now, but in each set, you can store 4 possible blocks. And if you're accessing ABCD, that's the only thing you do in life, you get 100% hit rate. But your address now looks like this. Your index is only 1 bit. And this is called a 4-way associative cache. As you can see, blocks with the same index can map to 4 locations, but your tag bits have increased again so that you can really identify what you're getting. And the likelihood of conflict misses are even lower right now. That's good. But unfortunately, the complexity is also higher. You get more comparators, as you can see, wider data mux, latencies increase because of this, and the logic also becomes more complicated. And the tag store is more larger because now you have 4 bits as opposed to 2 bits that we started with the direct map cache. And again, you can do the same thing that I just said, A, B, C, D, E, F, G, H now, and you get 0% again. How do you accommodate that? Now you're fully associative in this particular toy cache. Basically, allow any block to be placed in any cache location. That's the idea. And at the extreme, it looks like this with our 8 block cache. You don't have any index bits, basically. Indexing is gone. What you do is full comparisons of the tags. And it looks like this. You have 5-bit tags. So tag store is actually the largest in this particular case with this cache parameters. You have the maximum number of comparators. Every block, every tag needs to be compared. Every tag of the block that's stored, possibly stored, needs to be compared to the address. And logic here becomes more complicated. This is essentially, as you can see. Okay, muxes are also wider, right? Okay, does this make sense? Okay, with our simple cache now, we've eliminated the A, B, C, D, E, F, G, H problem. But of course, you can do this next. You can take the next step. Oh, what if I have the next 8 letters? Well, now you don't have enough cache, basically. You should increase the cache. That's where your next level becomes interesting, or you should consider increasing your cache. Essentially, what I've discussed is essentially set thrashing. What I just showed you is set thrashing. If you don't have enough blocks to house in a set, you're thrashing the set. So one way of actually reducing the problem is increasing the set associativity, but clearly you cannot increase it arbitrarily given a fixed size cache. At some point, you will need to increase the cache size, okay? Okay, so, but before we go into that, we talked about degree of associativity. Essentially, degree of associativity is how many blocks can map to the same index or set in the cache. Higher associativity usually gets you a higher hit rate. Of course, not guaranteed, right? This is very much dependent on your access pattern. Nothing is guaranteed because you get 0% hit rate if you do completely random accesses, right? You have temporal locality or spatial locality, you get 0% hit rate. Then you should consider not having caches. Okay, but in general, average across many workloads, you get higher hit rate. But you also get slower cache access time, both hit latency and data access latency, and you get more expensive hardware, more comparators. It doesn't come for free. And people have shown that you get diminishing returns from higher associativity. Across many workloads, you get a curve that looks like this. And this is a perfect industry slide because you don't have any numbers on either axis, right? It's a terrible scientific slide, as you can see, right? But I mean, I'm just showing you the shape of the curve, not real numbers over here. But of course, a given workload may benefit differently, right? A given workload may have 0% hit rate with a direct map cache, but may jump to, I don't know, 50% hit rate with a direct map cache, right? So it depends on the workload in the end. Okay, so we're going to talk about issues in set associative caches, but I think we should probably stop here. This is a great place to stop because this will actually open up a lot of design decisions. Plus, we're going to talk about other issues in general cache hierarchy design starting next week. And then we'll see how far along we'll get. Okay, have a good weekend. I'll see you next week.